this is for a brief recap. I think you remember last day we started phase restricted uncertainty, right? What was the platform? Because before that we discussed different type of uncertainties, but mostly they are all of norm bounded, right? Now, for if it has to be norm bounded, that means we mostly talked about the H infinity norm. In that case, your uncertainty delta S must belong to RH infinity, right? Because then only you can think about a valid and finite H infinity norm. Now, if it is not a bounded real uncertainty, then what will happen? That's what we were discussing. That is, suppose the uncertainty transfer function delta S, it has a pole on the origin or on the j omega axis, right? Say for example 1 by s or 1 by a square or 1 by a square plus 1. In such cases, we cannot apply the Small-Gain theorem, right? That's what we discussed, because Small-Gain theorem needs both the systems in the interconnection to be in RH infinity, and only in that case they will have finite H infinity norm, and subsequently we can apply the Small-Gain theorem to have the H infinity loop gain of the loop transfer function matrix remaining less than 1. Now the question is that if it doesn't belong to RH infinity, then what happens? So then we need some other techniques so that at least we can work with those kind of uncertainties, right? So that is the phase restricted uncertainty. That means you should not think that it doesn't belong to H infinity, that immediately it will imply phase restricted. It is not. Like for suppose for the class of uncertainties who are marginally stable, then if some of them have a phase restricted relationship, then at least we have some other techniques like negative imaginary or positive real to apply. Okay. Say for example, if it contains a pole at the origin 1 by s, or suppose if it contains a double pole at the origin 1 by a square, or if it is a suppose 1 plus a square plus 1, if delta s contain this type of terms, right? You can say that is uncertainty can contain many different terms. Yes, suppose I am not saying that it will only have this kind of terms. It may be, suppose delta s, it has a stable pole as well. Suppose 1 by s plus 1 plus 1 by a square plus 1. This is your delta s. We are modeling this delta uncertainty, and now you can see that it is going to be a third order uncertainty, right? Then you will see the ultimate the whole expression like a square plus s plus 2 divided by s into s plus a square plus 1 into s plus 1. This will be your delta s, and suppose that this is your delta s and I have split it into two terms. Okay. Now if you have a delta s of this kind of term, then due to the presence of a square plus 1 at the denominator, it doesn't belong to RH infinity. Now what will you do? That means what you will do means ultimately when you will have a M delta interconnection, whenever that is we think about a robust stability problem, or first of all, of course, the stability part will come into the picture. Then we have understood that is from the original given block diagram, generalized prime diagram, we have to represent it in the M delta, right? So this signal is Z or is Z delta, this you can write as W delta, right? So now our objective is to design, that means the main objective of designing a robust controller is that you have to design the K of S such that M of S, it belongs to RH infinity, and the interconnection of M and delta, they must be robustly stable, right? The first robust stability theorem that we learned is the Small-Gain theorem. So what does it say? That is, like if you can design this K of S so that MS is asymptotically stable, that means if I write here two objectives, and I hope like all of you know that, like still I am repeating, MS, the main two objectives of any robust control design is, first of all, you have to design K of S so that MS belongs to RH infinity, and not only that much, RH belongs to H infinity means this will serve the purpose of NS. NS means nominal stability, and secondly, for robust stability you need something more. So then what do you need? There is the H infinity norm of ms, it must be less than 1 by gamma, where we are assuming that is gamma is the maximum norm, or gamma is the bound of H infinity norm of delta of S, right? If it is so, then it is guaranteed by Smolgen theorem that this M delta interconnection will be robustly stable, right? It is clear for all of you. Now the question is that if this delta, if it doesn't belongs to RH infinity, then what would you do? We don't have any problem in designing this MS, because anyway the case, what case is in our hand, so we can design the K of S so that MS belongs to RH infinity. But if your delta doesn't belongs to RH infinity, then certainly you cannot apply the Smolgen theorem. That is, we are starting proving the robustability, right? Have you understood? So we have to search for some other robustability techniques, right? Robustability theorem for interconnected system. So there are some more. Say for example, this positive real, the passive passivitism is the non-linear setting. Anyway, the linear part is the positive real. The PR, SPR stability result, that is one of the things. Then NI, SNI stability result, that is another thing. All those things are robust stability result, right? One of them is PR, SPR stability result, or another one is NI, SNI stability result. Now from the definition, you can already see that it is positive real and negative imaginary. Both these systems or their system properties, they give us the phase restricted. They are examples of phase restricted systems. So last day, that is, we discussed all those things, like for the PR, positive real. If you think about the name, positive real, that means the real part of the transfer function remains positive for all frequencies. That's what the definition is. Re of Gj omega greater than equals to 0 for all omega r, right? Now you think about the simple, like the Nyquist plane. If this is real and if this is imaginary, we are saying that is this positive real class of system is those transfer functions whose real part would be always positive for all frequencies. That means their polar plot or even Nyquist plot will always remain confined in this side, that means right hand side of the complex plane, right? If it is so, then what is the phase restriction? This axis, this is plus 90 degree and this is minus 90 degree. So can't I say that is for PR class of system, the phase would be in the range of minus 90 to plus 90? We can say that is the reason why it is called phase restricted system. And then there is another subset within the PR is strictly positive real, for which the real part is strictly greater than 0. That means when you draw the polar plot or the Nyquist plot, it cannot touch the imaginary axis, right? Because touching the imaginary axis means the real part will become 0. Strictly positive real means the real part will always remain strictly positive for all frequencies, right? So for them you have to simply remove the connection, so you can think about that this is the part where the Nyquist plot will be there. Okay, so to clear up all those things, I have drawn plenty of examples. One by one we will understand, don't worry. So similar to positive real and analogous kind of systems have been designed, which is called, or have been promoted, that is called negative imaginary. If you now again stress on the word negative imaginary, what does that mean? The imaginary part of the transfer function will remain negative. That's what the definition says. Imaginary part of Gj omega, it is lesser than equals to 0 for all omega greater than equals to 0. Now this is the first difference between the definitions of PR and NI systems. Like in the PR definition, we don't have to restrict the frequency only to positive or negative interval, whereas for NI, we have to restrict the frequency interval. We discussed the reasons, okay? Today also from the examples, it will be clear. That is why, because last day we were discussing, if you have a real rational proper transfer function, and if you see the structure, then imaginary part 0 means always you will find that is imaginary part. If it is negative, then your Nyquist plot would be mostly, or rather not mostly, that is here only. That means below the real axis, right? Now, if it is below the real axis, now in most of the time it happens that is it is for only one range of frequency. One range means it is for positive frequency range, because if you would like to draw the mirror image like here, so of course that will be then in the other side, so then for which the imaginary part will become positive. So we cannot define negative imaginary property for the whole frequency interval containing both positive and negative. So that is the first difference between the definitions of NI and PF systems. Okay. Similar to SPR, here also we can define a strict class of systems within NI. That means your NI means imaginary part remains lesser than equals to 0. If you make it strictly less than 0, that means if it is strictly negative, then that subset is called strictly negative imaginary systems or SNI. Okay. From the examples they will be clear, don't worry. Now you can ask, that is why we are learning all this, because that is why we are learning. The main reason is we are looking for different robust stability results. Like if you have a, that thing also we discussed a little bit. Like if you have a negative feedback interconnection of a PR and SPR system, then its interconnection will always be internally stable, right? Similarly, in case of NI, if you think about a positive feedback interconnection of an NI and a strictly NI system, along with the DC loop gain being less than 1, then the interconnection will remain internally stable. So these two stability results we can apply directly in robust stability cases as well. Now you see both the PR and NI, they can contain marginally stable transfer functions, especially NI. Because that too we discussed, that is 1 by S, that is both PR and NI, right? But 1 by S square or 1 by S square plus 1, both of them have relative degree equals to 2, right? This is what is relative degree? 2 minus 0, 2. Here 2 minus 0, 2. You know PR systems can take relative degree only 0 or 1. So RD for PR, that is equals to either 0 or 1, whereas RD NI, that is 0, 1 or 2. That is genuinely an advantage, since NI systems can allow relative degree up to 2. So that's why systems like 1 by S square, 1 by S square plus 1, these kind of marginally stable systems are also, they also belong to the NI class. And now what is the advantage? Since we have this stability result, that NI SNI interconnection, so if somehow you encounter an uncertainty where this kind of marginally stable transfer functions are coming, then we can try to design this MS to become an SNI, so that finally you get an interconnection of NI and PR, NI and SNI here. Either PR or SPR or even NI or SNI, right? Then actually we still have the robust stability result, and we don't need the help of Molgier theorem. So in that way we can extend the class of systems for which we wish to establish the robust stability, right? Have you understood? That means like we are learning about phase restricted uncertainties to increase our class of uncertainties for which we can establish the robust stability, right? If you have a delta which doesn't belong to RAT infinity, for them we have to search for some techniques so that we don't remain handicapped, right? That is the main motivation for learning all of them. Now that is already we discussed, but it's just a brief recap. Now coming back to the example, because we should develop a clear understanding about the NI and PR system, so that I have drawn like many of the polar plots. This main intention is to look at the plots carefully and then to decide that is which kind of systems they are. Okay, and also that is you suggest what would be the transfer function. Starting from this one, can anybody tell me whether this is PR or NI or both? PR. Why are you saying PR? Because the real part is all positive, or here it is 0, but at least not negative, right? So that's why it is PR. Okay, fine. Is it SPR as well? Because at one point at the omega equals to 0, it is starting from origin, so the gain is 0, right? The real part is 0, so that's why it is not SPR, it is PR. Is it NI? Because imaginary part is positive, so that's why it is not NI. Now, can you tell me that what is the structure of the transfer function? No, I mean what will be the transfer function? Pole zeros. Don't have to tell me the numerical values, just a structure. What is the pole and then what will be the zeros? Starting from 0 means it must have a 0 at the origin, and then ending on the positive real axis means that is it must have a finite pole, because it is when you have a 0 at the origin it will give you plus 90 degree phase, and ultimately ending on the axis means it is 0 degree, so you must have a pole to compensate that plus 90, right? So this transfer function would be S by S plus P, P positive. So this is the transfer function for this kind. Now coming to the second one, again it's PR, right? But what is the difference?
SPR.
Exactly, it is SPR. Here you can answer, sir, why didn't you write PR comma SPR? SPR means by default it is PR, because SPR is a subset within the whole PR, right? So if you write a transfer function to be SPR, that means inevitably that is PR. Now, what is the difference between that? Only this gap. What does that mean? Now it has a 0 but not at the origin. It has a finite 0. So what will be the structure of the transfer function? S plus Z by S plus P. But Z is less than P. That is very important. S plus Z by S plus P. Now 0 greater than Z. 0 less than Z less than P. That means 0 must appear before the pole. Can you tell me that if it is flipped, that means if the pole arises before the 0, then what will be that shape? I said that is if the condition is flipped, that means if the pole appears before the 0, then what will happen? Then it would be like that. In that case, that it is instead of the first quadrant, now it is on the fourth quadrant. So in that case, the structure will remain the same, S plus Z by S plus P, but now P is less than Z, right? And in that case, it will be both NI and PR, because it is in the fourth quadrant. Now you see, real part is positive, imaginary part is negative. So if you see a polar plot which is completely on the fourth quadrant, then it will be both NI plus PR. Isn't it? Once again, that is here, real part is positive, that's why PR, imaginary part is negative, that's why NI. So if you have a transfer function whose polar plot lies on the fourth quadrant entirely, because if any part, even if a small portion goes into the third quadrant or comes into the first quadrant, immediately one of the property will get lost, right? So if it is completely on the fourth quadrant, then it is both NI and PR, fine? Or rather, not only NI plus PR, like SNI and SPR, okay?
Lots of SN, not SN, not SN, only SN.
Why? SNI, see the definition?
So, imaginary part can be 0.
That's why there is 0 and infinity. Those two things are excluded.
Yes.
You please check your notes last week. That is, we discussed why those two borderline frequencies are excluded. Because for any real rational proper transfer function, the imaginary part will always be 0 at omega equals to 0 and omega equals to infinity, right? That's why we cannot define the strictly negative imaginary property keeping omega equals to 0 and infinity. Okay? So this should be both SNI and SPR. Okay, fine. Now coming here, what kind of, here it is spread across both these quadrants, so certainly we cannot call it NI, but it is PR, right? Now we have to check whether it is SPR. Can anybody tell me what is the structure or configuration of the transfer function? How many poles and how many zeros? 2 poles, 1 0. Like its structure would be S plus Z divided by S plus P1 into S plus P2. And if the polar plot doesn't migrate into the third quadrant, then like there is a specific condition like Z lesser than equals to P1 plus P2. Under this condition, you will see this kind of graph. That means, of course, the 0 should appear both the poles. It can appear in between the poles also, but in that case it will remain PR but not SPR. Now this one, the same configuration, but here what will happen? In this case, say I think here it will be greater than P1 plus P2. In that case, it will.
It's third order, right? It will be third order system.
No, here it would be second order only, because when this is going like this only, not here, that is the ending would be at minus 90. That means two kind of things can happen. Good question, Manish. One thing, the ending can be like that. So when it is ending, it will be at minus 90. Another ending is like then ending at minus 180. For that I have drawn this figure. Here you will have one more pole. So for this one, actually this is S by S plus P1 into S plus P2 into S plus P3. Why here you have a S? Because it is starting from the origin. It is starting from this point, okay? This is at omega equals to 0 and then ending at minus 180. So that means 0 will offer plus 90. So there must be 3 poles, and that is the reason why it is ending at minus 180 degree. So in this case, it is still PR. In some cases, it can be SPR as well. That depends upon the placement of the 0 and like the relation between the poles and the zeros. But now what happens in this case? It is neither purely NI nor purely PR. Please be careful about that. It is neither purely NI, neither purely PR. This is a new category called mixed NI plus PR. What does that mean? That means for some frequency interval it would be NI, for some it would be PR, and for some it would be both. Like you see, when it is in the first quadrant, if this frequency is omega 1 and this frequency is omega 2, from 0 to omega 1 it is purely PR. From omega 1 to omega 2 it is both Ni and PR, and omega 2 to infinity it is only Ni. These kind of systems are called mixed Ni plus PR systems, which is neither purely Ni nor purely PR. Okay? So both this, like this one as well as this one, both this will fall in the category of mixed Ni plus PR. Now this one, this is simply K by S plus P. It is both SPR as well as SNI. P only on the fourth quadrant, so it is both SPR and SNI. Asa, can you tell me that is what would be the difference in the transfer function between here and here? Because both of them, I said that they satisfy both SNI and SPR. But looking, there is slightly difference in the polar plot, right? It is ending on the origin and it is ending on the real axis. So, what is the difference?
Denominator only S like that.
No, in denominator it cannot be S, because in that case, if it is a pole on the origin, then that is it cannot be a bounded polar plot, right? Because if S goes to 0, then that will go to infinity. I give you a hint in terms of strictly proper or biproper.
So S plus Z divided by S into S plus P.
It cannot have a S on the origin. If there is a pole at the origin, then what will happen? At low frequency, it will start from infinity, like this plot. This one. This is the K by S into S plus P.
So S plus Z numerator.
If you have a pole on the origin, of course you make S tends to 0, then you see what happens. It will start from infinity. So here the what is the difference?
This one is strictly proper transfer.
Only difference is that the pole zero combination is something like that. That in that case it is a strictly proper like K by S plus P, and this is biproper S plus Z by S plus P. That is the difference. For any strictly proper transfer function, you know that it will terminate at the origin, right? But if it is biproper, then the gain at infinity would be either like positive real number or a negative real number, right? So it is ending here. So at infinity, it's a positive value. So that means if you see the D matrix of this, it would be positive. So that is the only difference. It's a biproper transfer function. This is a strictly proper transfer function. Now this one here, what is the structure? K by S square plus P1S plus P0. Very standard second order SNI example. It cannot be PR, right? Can anybody tell me what is the structure of this transfer function? One more pole. Huh. Here you have one more pole. Suppose S plus P3 into S square plus P1S plus P0. Right? And in this case, it is neither PR nor NI. You can say that is, sir, it seems that it will belong to the mixed class, right? But here still it is finally going into the second quadrant, so not even a mixed. So this is, you can say that is starting from the zero frequency, and if that is omega c, so from 0 to omega c it is SNI. But purely it is if a system is not purely NI or PR, we cannot say that is a NI or PR. Okay. Either mixed, or else you will have to say that it doesn't belong to the NI or PR property. Okay. Now that is, you might have a confusion here. You can say that is, suppose this is frequency omega equals to 0. This point it is omega c. Now you can think about, this is also a mixed NI plus PR system. That is, in the fourth quadrant from 0 to omega c, it is both PR and NI, and from omega c to infinity it is NI. So can we say that this is instead of SNI, or even in addition to SNI, can you say this is also a mixed NI plus PR? This one. From 0 to omega c, it is both PR and NI. Omega c to infinity, that is NI. So in that case, can we say, or should we say, that it is also an example of mixed NI plus PR? Adhavi, what do you think? Why not?
Which relative degree is you have to do?
That is a good point. Relative degree is 2, and one more point.
In what also it is purely PR, so we can also do
That is, when you see a polar plot, first you have to check whether it has purely PR or purely NI property. See, in these two cases, I said they are mixed NI plus PR. All of you please look at the board. For these two examples, I said this is mixed NI plus PR. Why? Because first of all, you will have to see that whether it is purely NI or purely PR. If both of them fail, then only you check whether it can belong to the mixed category. Once again, first you check whether it is purely NI or purely PR. If it fails to be fails to be any of them, then you see whether it belongs to the mixed class. Okay. So in this case, for k by a square plus p1s plus p0, already we can see that it is purely SNI. So no question of going into the mixed category, right? Then after that, this one, as I said, this is like PR or NI, both of them are not possible. Then this one, it is simply k by s, single integrator, NI as well as PR. Then after that, k by s into s plus p. This cannot be PR, but this is NI.
So
Right.
K by S, can it be SNI?
No, because SNI systems are defined for only asymptotically stable systems. And here you will find that is, although I have drawn the graph like that, you will find the real part will be very minimal. And please note that both SNI and SPR, those systems are made for asymptotically stable systems. Okay. So this is NI, this is NI for then not NI, not PR. This one again not NI, not PR. This is 1 by S square, so this is NI. What is the transfer function of this category? K by S into S plus P1 into S plus P2, right? Now coming here, this must be 1 by S cube, right? Not NI. This must be 1 by S to the power 4, again not NI. Right, good question. Can it be pair? Okay, this one also. This Ni, of course not, but can it be pair? What do you think? Confusion happens, but at this moment confusion is happening because we have drawn only the polar plot. If you complete the Nyquist plot, then you will find from 0 plus to 0 minus, it will have total like 3 rotation, total 360 degrees. So how many? That is pi, 3 pi rotation. Because you know, like depending upon the type, for n equals to 1, it gives minus pi, right? When you close the, what about the Nyquist plot? It has 4 segments, right? Then omega 0 plus to plus infinity, then plus infinity to minus infinity to minus 0 to 0 plus. And that we maps into the Nyquist GH plane, right? So there, when the omega 0 minus to omega 0 plus it closes, then for type 1, for each type it gives or it takes minus pi. Minus pi means clockwise pi degree or pi radian, 180 degrees. So here you have type 3. So type 3 means it will take 3 pi rotation, right? That means 1 full circle, 1 more. So that's why, and then from the definition, how do you check? Relative degree 3. PR system at max it will take 1. For PR system, relative degree at max it is 1, and for Ni at max it would be 2. So for systems 1 by S cube, 1 by S4, they cannot be Ni or PR. Okay? Then if you say that is sir, from the definition can't we find? Yes, from the definition also we can find. Here the definition what I have written, that is the simplest definition. It is not the full. That is for the frequencies where there is a pole, we cannot directly write this condition, right? Because suppose if it is 1 by S square, can you write that is real part of Gj omega at omega equals to 0? Because it is infinity, we cannot write. So what do you need to do? At all such frequencies, you have to check the residue of the transfer function at those frequencies. And the residue has to be non-negative. So in that way, if you check, then all those systems will come non-Ni or non-PR.
Also, we can do that RE of Gi omega should belong to R. That will also I think.
Here, when I am writing that is greater than equals to 0, lesser than equal, or strictly greater than 0, that means it is positive real number only. It cannot be infinity. So here, that is, this is the simplest form of definition where, and these are for asymptotically stable system. The moment you have a marginally stable system, you have to exclude those frequencies where you have a pole. And then, and all those frequencies you have to separately find the residue, like Cauchy residue theorem, residue at that frequency. And if it is Ni or PR, you will find that is a residue at that frequency will be non-negative. From that we check. At the beginning I didn't write the full formula, full definition, because it would be unnecessarily very complicated. This one is probably minus 1 by S, right? You please check it later. Here it is almost like same like that of this, but the arrow is like or no, this will be probably minus S. Minus S. that is not also PR, right? Now, if you see this one, this is a little bit complicated transfer function, but this is one of the
So class
classes. And starting
from 0
Uh-huh.
0 going to
If you consider improper PR system, then you will see that this is an improper PR system. As of now, we are like doing everything for real, rational, proper, but PR or NI systems can be defined for improper systems as well. So it is an improper PR system with relative degree equals to -1. That you can write. As I said, that is the PR or SPR, sorry, PR or NI, they are defined for improper systems as well. Although that is we mostly learn real rational proper system, but it can allow -1 as well, and here -1, -2 as well. So this S there you can write that is it is an improper PR system with relative degree -1.
so now S transfer function will be now no PR no
Huh. If we don't take improper, what I said that is either you say that is that if the definition is restricted only to real rational proper, then S is not a PR. But if the improper is allowed, then you call it's a improper PR or PR with relative degree -1. Okay. Now, so when you write a PD controller, what is the transfer function? KP plus S into KD. That is a PD controller. This is a PR with relative degree -1. So this is a PD controller. When you write a PI controller, what is the transfer function? KP plus KI by S. So this will be SKP plus KI by S, right? This is a biproper PR but marginally stable. KP plus KI by S. So it is SKP plus KI whole by S. This is an example of a biproper PR transfer function but marginally stable. Why marginally stable? Because you have a pole at the origin. This is one of the most important example in the NI literature, because finding a non-strict NI system is not a easy task. So in there, like so far, there is only two types of non-strict NI systems we have seen. One is this and another one is this. So this is the transfer function, which is this one. Why that is I am saying very important, because most of the asymptotically stable NI transfer functions which we come across, they are SNI also. But asymptotically stable NI but not SNI is this one. So what I am saying, this transfer function is asymptotically stable NI but not SNI. That's why it is very important. And constructing such an example is really difficult. Why this is NI but not SNI? You see, at this point, omega equals to 1, the polar plot is touching the real axis. That means imaginary part is 0. So at a finite frequency, imaginary part is 0 means it is not SNI, right? So that's why it is SNI and this is asymptotically stable, but it doesn't have strictness. Similarly, this other one also. This also, that is here you can see the two loop happening on the origin. Here also at this particular frequency, it touches the origin. That means both real and imaginary part, they are 0. So since imaginary part is 0, it cannot be SNI. Okay, but this is also asymptotically stable NI. Can anybody tell me what is this transfer function? This is very ugly, I know, but what will be the transfer function? This has a similarity with one of them. So what you were thinking, that is
Twice.
that is this one has been multiplied with a 0 at the origin, that is plus 90° shift. All of you try to think, if this whole one is given a plus 90 shift, it will become like that. So this transfer function into S, that is the polar plot case. So it will be an example of an asymptotically PR system that is not SPR. You check all of them and ask me if you have any doubt. Exactly, you have to leave, right? PR is PR का डेफिनेशन सबसे इजी कौन सी जगह पे है? सबसे इजी, एक बार पढ़ने से समझ में आ जाएगा। जैसे they ask that what is the full definition. So full definition means that residue condition must be there. So in which paper or which book we can find that full definition? No, easily लिखना पड़ेगा because otherwise all beginners will face challenge. हाँ, आप तुम्हें लिखना है. Is it fine for all of you? Any doubt so far? I am now going to state the stability theorem, and then after that we will start this our most intended topic, that is H infinity controller synthesis. First we will learn state feedback H infinity. After that dynamic output feedback. Do you remember the full definition? याद है? अकेले लिखोगे? स्टेटमेंट बाकी लाइन बोलो. सपोजिशन मैं लिख दिया एंड देन रिजल्ट बोलो. व्हाट इंटरकनेक्शन? साइन बोलना पड़ेगा ना. देन द नेगेटिव फीडबैक इंटरकनेक्शन ऑफ G1 एंड G2 इज बस उतना ही, क्योंकि इधर तो और अनसर्टेनिटी नहीं है ना. एक अनसर्टेनिटी हो सकता है बट वी डोंट नो, इट इज ओनली पीआर एंड एसपीआर. नितिशा बोलो, सोच के बोलो पूरा क्या होगा. सपोजिशंस लेट G1 be Ni एंड G2 be SNi, बट उसके साथ हम लोग और भी कुछ चाहिए. ठीक है ना, वो तो बाद में आएगा. सपोजिशन में वी नीड समथिंग मोर व्हिच वाज नॉट देयर इन केस ऑफ पीआर. spit out this statement and you tell me what you have understood. NISNI stability theorem is a little bit complicated compared to PR-SPR. Okay, why you have already understood, that is, it has some extra conditions, right? I will explain. Don't worry. What are the differences? One by one, you tell me. Just you check both of them side by side and you try to identify the differences. Once again. Right? Here the only thing is that G1 be PR and G2 be SPR. Other than that, we don't have any extra conditions, right? If one is PR, other one is SPR, then their positive, negative feedback interconnection is internally asymptotically stable, right? It also has a big advantage. Say for example, that is G1, it has the poles and zeros along with a gain K1. Similarly, G2, it has a open loop gain K2. Then this K1 and K2, they can be made arbitrarily high or arbitrarily low. The property will still exist. So this PR-SPR stability, it is called a phase-based stabilization, because everything here depends upon the phase. So this is called a phase-based stabilization. Okay, it doesn't depend upon gain. So suppose one of them is a controller and you need a high gain, you are increasing K1 and K2, you are safe. Whatever, as long as they are PR-SPR, they will remain internally stable. Even if you increase the loop gain, that doesn't cause any harm to the stability. Okay, that is one of the main advantages. So this result is completely phase-based stabilization. So here P1, P2, they can be made arbitrarily high. NISNI stability theorem, what are the extra things or what are the extra conditions that we can identify? That first of all, I started with let G1 be a strictly proper NI system, right? So this strictly proper means the gain at infinity is 0. That is the condition, G1 infinity 0. Now this theorem has two versions. Two version means ultimately result will remain the same, but this supposition part can be of two types. One is either you directly say G1 is strictly proper, that means this one, right? Or you have to satisfy both these. That means loop gain at infinity frequency is 0. That means in this case G1 is not strictly proper, but G2 is strictly proper, right? Because if this condition has to satisfy, then one of them has to strictly proper. So in the second case, now suppose G1 is not strictly proper, G2 is strictly proper. In addition, this one G2 infinity greater than equals to 0. possibly वो G2 0 था या infinity 0 था. Sorry for the typo. In this case, along with this condition, that is G2 0 greater than equals to 0, that is the DC gain of the G2, it must be positive. Okay. At this point you may be surprised, that is how could it happen, that is either this one or these two. That is, if you ever see the proof, then from that it would be clear, that is either this one or the conjunction, the combination of these two will make the purpose for us. Okay. So now that is, so here what is this property mostly about? The gain of the system at infinity, right? So this strictly proper, that means G1 infinity is 0. Even in the second case, we are trying to ensure G1 infinity into G2 infinity equals to 0. That means we want that the loop gain at infinite frequency should be 0. Because you see, whether you have the first one or you have the second one, in both the cases, loop gain at infinity will be 0, right? Here G1 infinity 0, so G1 infinity into G2 infinity 0. In the second case here, it itself is guaranteed G1 infinity into G2 infinity 0. So that is, we want that the loop gain, if LS is the loop transfer function, that is loop gain at infinity, it must be 0, for which one of the system must be strictly proper. That is one of the main assumption. Okay. If that is so, here I have kept dot. We need something more. I will come later. At this moment, don't worry. So let G1 be a strictly proper NI system, something which I have interpreted, and G2 be SNI. Fine. Then this is the result part. The positive feedback interconnection of G1 and G2 is internally asymptotically stable if and only if the loop gain at 0 frequency less than 1. That means that is that if I write for CISO systems, it is L0 less than 1. This is called DC loop gain condition. That means loop gain at 0 frequency. That is the main condition for NI-SNI stability. L0 is less than 1. Okay, you can ask that, sir, if this is so simple here, why you are writing lambda max, that means why is this required to bring lambda max? Because for MIMO cases, G10 into G20, it's a matrix. You cannot certainly write a matrix less than a scalar value, right? That's why it is required lambda max of that matrix less than 1. That is the main stability condition. Okay. Now you see the difference. In case of PR, SPR, what we needed only this much, that one is PR, another one is SPR. But in case of NI, SNI, that is not only the situation. Of course, here one is NI, another one is SNI, but you need some more. Like first of all, that is this one of them must be strictly proper, that is a supposition, so that loop gain at infinity is 0. And then finally, the main stability condition, that is the DC loop gain less than 1. That is L0 has to be less than 1. So that is the reason we call NI-SNI stability theorem is a conditional stability result, whereas PR-SPR is an unconditional one. Please write this as a note. PR-SPR stability result is an unconditional stability result, while NI-SNI is a conditional one.
Sir?
Yes.
in the assumptions,
Huh.
the or part, why do you need to write G1 infinity? Because in that second middle line,
Huh.
G1
Then
infinity.
either only this condition or these two together. That is the meaning.
So, but if these two together are 0, then either one has to be 0.
Huh. But here
If we
the
had G2 equal to 0, then also it will be sufficient.
here yes, but the condition it goes like that only. That is ultimately what we need to show, that is a loop gain at infinity equals to 0. That is, in this case actually what happens, that is, if you go by the second condition, then here also G1 infinity can be 0. Actually this version came much earlier, this came later. That is, this version, so from 2008, 9, 10, at the very beginning of NI theory, because NI started in 2008. So this was the original version of the theorem. Later, the people saw that is okay, these two can be like instead of putting these two conditions, if we directly make G1 0, then our purpose would be served. But certainly you might think that is okay, if this is the condition required, then if any of the system becomes strictly proper, then our purpose is done, which is quite intuitive. But no, in the proof, that is, we need either G1 to be strictly proper or this combination. So this G1 in this result, this came 2017. I have written the shorter one so that you can easily remember, but I could have written the first one only, which was the original result. And finally, that is, you have seen the positive feedback interconnection of G1, G2 is internally asymptotically stable if and only if lambda max of loop gain is DC loop gain is less than 1, right? So I hope you have taken the note that NISN stability theorem is a conditional stability result, while PRSPR is an unconditional stability result, right? Just as a small example, if you consider this one G1 this and G2 this, can you tell me that according to the theorem whether this will be stable? Why? First of all, you have to check whether these two systems are satisfying the conditions of the theorem, right? So here G1 and G2 both are strictly proper, so the best case for us. So automatically the assumptions will hold, right? Then you have to directly go back to the condition. Here what is the loop gain? G1 0 means 1 by 5 and G2 0 means 1. So it will be 1 by 5 less than 1. That's why it must be stable. Now instead of this one, if I make it 5 by s plus 1, then it will be the borderline case. That is 1 by 5 into 5 equals to 1. In such cases you will find one, like the closed loop poles, it won't go to right hand side, but it will come on the j omega axis. That is the interpretation. It has to be less than 1. The borderline case means when L0 equals to 1. Those are called the marginally stable cases. That means one, you will find one pole pair of the closed loop transfer function will be on the j omega axis.
Sir, can you give us one?
Huh?
Can you give us one?
Sure. they won't. This afternoon, I went to the hospital to take an antidiabetes injection. And then the doctor asked, that is, how did the dog bite happen? I said that is काल रात डॉग्स को लड़ाई कर रहा था तो मैं बचाने के लिए गया तो देन डॉक्टर बोला सच में तो आप पागल है क्या मैं बोला नहीं उसमें एक्चुअली मेरा डॉग भी था तो मैं छुड़ाने के लिए गया था तो देन उन्होंने बोला डॉगो पागल मानुओ पागल
So they have to classify class 1, class 2 like that.
आपको भी रेबीज
You have to take medication next week.
No, not one. First day, third day, I think fifth day, no, first, third, 7th, 21st, and then after 1.5 hours. But I keep on taking after every 1.5 year. Because I have pets and that you know, इसका पास पेट रहता है वो तो कुछ scratches या bite तो होता ही है.
खाना में restriction है क्या?
ना. तुम्हें लेना है? Do you have pet?
पर एक वो है कॉलोनी की पेट मतलब कैट है जो सब में घूमते रहते हैं और काटते रहते हैं हाँ उनको वो बहुत लोग हैं ना जो पूरा उनको फ्राइड फिश देते हैं एकदम बाप रे बाप पहले मतलब जब था तो हम लोग के घर पे जो बाकी रहता था वही देते थे वो खा लेता था अभी मतलब सबका कह रहा हो गया था फ्राइड फिश खाता था कुछ नहीं खाता
और उनका किस्मत बहुत अच्छा. If we have this interconnection, simply there is a unity positive feedback interconnection of 1 by s plus 1. Will it be stable according to NISNI stability theorem? Vidisha, what do you think? This one is stable?
If it is strictly proper, then
Don't ask me, because everything is written in the book.
मार्जिन
थ्योरम के साथ कंपेयर करा के देखो क्या होगा. पहले देखना पड़ेगा कि whether this interconnection satisfies all the required conditions and then whether the discrete condition holds or not.
one has to be SNI.
1 by s plus 1, that is SNI. No problem.
One
A9.
and
So the theorem remains applicable. Now the question is that will it be stable or not?
DC plane
What would be DC plane?
one.
That means not stable, right? So this kind of question is a little bit tricky, right? So that's why I gave an example. Next, suppose s plus 2 by s plus 1, that is also a SNI, right? Now, what would you say about this stability? Can you apply the NISNI stability theorem to this case? First, you think about that.
No, sir. It is not stable.
Strictly proper condition is not.
That's what. if this kind of thing comes in the exam, you have. That's why that I gave you these two examples. Whenever you see an interconnection for any stability theorem, first of all you have to check whether it is satisfying the assumptions. If everything is fine, that means that you can apply the theorem. After that you go to the checking condition, that means the end condition. See, 1 by a square, they are also Ni. Now, if you have one of the system, I mean the Ni system having poles on the j omega axis, especially at the origin, then what will happen? Other one, suppose G2 SNI, but G1, it has a pole on the origin. Then can you apply this theorem, this version of the theorem to an interconnection with the Ni system having pole on the origin?
So they will blow up. Okay.
Exactly. That means if the Ni system contains a pole at the origin, then this version is not at least applicable, right? Try to understand the situation. What did I say? If one of the system in the interconnection contains a pole at the origin, then the version which we just learned, this is not applicable. And now can you understand? That is why I have kept this place blank. That is what should I write? What do I need to write here? Let G1 be a strictly proper Ni system without any pole at the origin. This is really important. See, I could have written that part directly, but in that case, you wouldn't have understood the necessity that is why this part is coming. So that's why I kept it blank. Now you have understood that is why this extra clause is highly important in this version of the theorem, because NISNI stability result has two versions. We have learned version 1, now we are going to learn version 2.
So what if G2 has pole origin?
G2 cannot, because at least one of them has to be SNI, and SNI is always defined for asymptotically stable systems. Asymptotically stable means it cannot contain any pole on the j omega axis. The other type of marginally stable case, for example 1 by a square plus 1, that is an Ni system, it is marginally stable, but at least it doesn't have pole on the origin. So that class of Ni systems is allowed in this theorem. So in the first line says that is let G1 be a strictly proper Ni system without any pole at the origin, but it doesn't say that it cannot have any pole on the whole j omega axis. That is the difference. So if you have a marginally stable Ni system without poles at the origin, that too is fine. in the second case, what would be the version? Let G1 be a strictly proper NI system with one or two poles at the origin. হ্যাঁ শুনবি আমি ক্লাসে রয়েছি আমি 9টার পরে ফোন করছি ঠিক আছে কিছু ইমার্জেন্সি হয়েছে নাকি আচ্ছা আচ্ছা ঠিক আছে আমি রবিবারে যাব ঠিক আছে হ্যাঁ 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 রবিবারে যাব চিন্তা করিস না ঠিক আছে হ্যাঁ হ্যাঁ ওকে So the version 2 that I am first stating and then you tell me whether you can understand. So it will be almost the same but ultimately the condition will become different. So if I start from the beginning, let G1 be a strictly proper NI system with one or two poles at the origin. Here we are specifically mentioning that the system has a pole at the origin. Why? Because if you keep it open, then actually it may mean that the other case is also included, but in that case what would happen, the new condition which we are now going to learn, that doesn't apply to these cases. So that's why we are separating two versions completely. So here specifically I mentioned without any poles at the origin. In the second version we will mention that is it will have poles at the origin, and an NI system can contain maximum 2 poles on the origin, not more than that, because in that case the maximum relative degree 2 condition will be violated. Once again, an NI system cannot contain more than 2 poles on the origin, because in that case the relative degree constraint or the phase angle constraint of 0 to minus 80 degree will be violated. So that's why, okay, you first write it there, then I will start. So what was the first line? Let G1 be a strictly proper NI system with one or two poles at the origin, and G2 be a G2 be an SNI.
So for G1 will not be NI.
NI,
G2 strictly
G2 SNI, that means strictly NI. Once again, that is let G1 be a strictly proper NI systems with one or two poles at the origin, and G2 be an SNI system, or simply write G2 be SNI. Then the declaration part is over. Now we will write the final result. So what that will be? Then the positive feedback interconnection of G1 and G2 is internally asymptotically stable if and only if. What would be the new condition? G0 less than 0. That means G0 is negative definite. That is the stability condition. If and only if G2 of 0 is negative definite. हेलो हाँ भैया पहुँच गया अच्छा ठीक है आपको 4-5 तो मैथमेटिक्स डिपार्टमेंट पे आके उधर ही वेट कीजिए ठीक है हाँ So what was that condition? It is simply G2 0 less than 0. That is the stability condition. Okay. Let's take an example. Suppose your G1 of S, that is 1 by S square. Okay. Now here what is the speciality? This is going to be an SNI systems for which the DC gain is negative, which is not very common, right? Most of the systems we see in practice, they have positive DC gain. So that's why this class of systems we do not readily see. So can you give me an example of an SNI system with negative DC gain? We have already learned many different type of SNI systems. But can you construct an SNI with a negative DC gain? even in that case also decision won't be negative, right? So Darshan, you gave a good one because that is a kind of system which is called non-minimum phase SNI system. For example, 1 minus s by 2 plus s. Everybody please look at the board. This is also an important class of system which is called non-minimum phase SNI system. Like 1 minus s by 2 plus s, of course it is a non-minimum phase system, and on top of that it is SNI. If you draw the polar plot, it would be like that.
So if it is s minus 1, then it will be negative.
Then if it is s minus 1, then it won't be Ni. That is the problem. So here this is omega equals to 0, this is omega equals to infinity. So that kind of polar plot, that is, it is starting from the 4th quadrant and it is ending on the 3rd quadrant, but it is biproper. So this class of system always you will find they appear in a biproper format. You can increase the number of pole 0, but it will always maintain relative degree 0. That means you see here you have one pole 1 0, then similarly you can add one more stable pair of pole 0. Then that way you can increase the order, but you have to maintain the relative degree. Okay, so this is called non-minimum phase SNI. But now this is another class of. How do you construct? You simply, the structure is minus of s plus z by s plus p, but the condition would be flipped. When we write an Ni transfer function s plus z by s plus p, pole should come before the 0. Now it has to be reversed. 0 will come before the pole. So here 0, you have to maintain this condition. If it is so, then it would be an SNI. So one example you can easily write, suppose minus of s plus 1 by s plus 1. This will be SNI, okay? But now that is, there are 2-3 points which are really essential to observe. Let's say this minus sign is not there. That means minus of this versus s plus 1 divided by s plus 4. What is the difference? S plus 1 by s plus 4, this is not at all Ni. This is a PR system, rather SPR system, right? S plus 1 plus s plus 4, this is a biproper SPR system, not even Ni. Whereas the same transfer function being multiplied with minus 1, that means you are giving minus 180 degree phase shift. Now it is becoming Ni. That means that is s plus 1 by s plus 4. If you draw the polar plot, this is the polar plot when it is SPR. And now for the other case, you will have this plot. So this is s plus 1 by s plus 4. This is minus of s plus 1 by s plus 4. So that is a big difference. So in that way, you can construct minus of s plus z by s plus p. You can increase the pair also. Suppose here s plus z by s plus p, then s plus z1 divided by s plus p1, and you have to maintain that relation. Maintain that relation means suppose g2 of s, I am writing minus of s plus j1 divided by s plus p1 into s plus p2 into s plus j2. Here, that is how would you decide the pole 0 pairs? So 0 less than p1 less than z1 less than p2 less than z2. In this way you can select. उल्टा होगा ना? Not only that, it will always contain real pole zeros, it can be complex conjugate pole zeros as well, like s square plus z1 s plus z2, here s square plus p1 s plus p2. that too cannot. So this is another version of the NI-SNI stability theory. Okay. Now we already discussed. Like today, I am not going to start the H infinity because it is already 7:15. But you see why that is learning the H infinity framework is required, because you have already understood that with only H infinity framework we cannot succeed, because if the uncertainty, if delta belongs to this marginally stable kind of uncertainties, we need these other results as well, right? Now the question is that when you have the M delta framework, now H infinity means finally it will apply small gain theorem. So MS will, Ks is designed such that MS will belong to RH infinity and its H infinity norm has to be less than 1 by gamma, right? Provided the delta belongs to RH infinity and its norm bound, maximum norm is H infinity norm is gamma. Now, if the uncertainty belongs to Ni or Pr, then you have to design Ks so that MS becomes SPR if you wish to use the PR-SPR framework, or MS has to be designed to be an SNI if you wish to apply the NI-SNI result, right? Are you getting what I am saying? So now that is, you have to learn the general framework by which you can develop the set of LMIs so that ultimately you can design either an RH infinity object or an SPR object or a SNI object. Are you getting? That is, if it is H infinity framework, then you are designing Ks so that MS becomes MS belong to RH infinity, and then H infinity norm would be less than 1 by gamma. Now, if that is in the PR framework, then what will be your control objective? Like case 1, H infinity framework. So here your first objective is that you design your Ks or the controller so that MS belongs to RH infinity and H infinity norm has to be less than 1 by gamma, right? This is clear to all of you, we have already learned. Now if you wish to apply PR framework, then what is your objective? Simply you have to design the K of S so that MS is SPR. No extra condition is required. Okay? Case 3, NI framework. What is your objective? First of all, MS has to be SNI. Right? And lambda max of delta 0 in 0 less than 1. In this case, always we'll have to take the help of the first version. M delta. You were talking about the infinity condition, right? Here I have assumed that is the delta is strictly proper. Now, if delta is biproper, then here you have to design Ks so that MS becomes a strictly proper SNI. Here I assume that is delta S is a strictly proper uncertainty, okay? And before that, you should always have that M delta diagram so that you can easily relate. It can be plus or minus. This is Z delta, this is W delta. Okay. In the first case, when delta S belongs to RH infinity, we are proceeding with H infinity framework. In the second case, if delta belongs to, if it is a PR uncertainty, then we will apply the PR framework. If delta is a NI uncertainty, then we will apply the NI framework. And in each case, these are the objectives for which we have to develop the LMIs. Okay, so that by solving the LMIs, finally we can design that K of S. Our ultimately objective is to design the controller K of S, a dynamic controller. It can be static controller as well, either a state feedback or a dynamic output feedback, so that these are satisfied. Because ultimately our aim is to achieve or to maintain the robust stability, right? At this moment we are not talking about the performance, only robust stability. So these are the different robust controller synthesis framework. Earlier we learned many things about analysis. Now we are going towards synthesis. Synthesis means controller synthesis. Okay. So we will. That's why that is. We will learn the H infinity framework in detail, both state feedback H infinity design and then dynamic output feedback H infinity design, so that later if you have to learn PR or NI, it doesn't create any problem.
So, and I think version 2 of NISNI. So, what about the DC loop?
That is, DC loop gain doesn't exist, right? Because one of the system has a pole at the origin. That's why DC gain doesn't exist. So the other one, it depends upon simply DC gain of the controller or G2. That is the changed version. Still, that is, you will have some doubt, we all, because at this moment we are not learning the proof of those theorems. Those proof was really lengthy. I will share the papers, you can just have a glance at it, but in the class I won't give time to do the whole proof. But unless and until you see the whole proof, the doubt will always remain there, that is why this particular thing is coming. But we are learning the results at this moment because we don't have that much time to learn the proof. Okay guys, today we are stopping here. Tomorrow from